Okay, everyone. I just wanted to let everyone know that this webinar will be recorded. So if you have any problem with it, please just let us know. I will start the presentation now. Okay. Hey everyone, welcome. Thank you very much for joining us today into the Unlocking the Power of AddPath webinar. It's wonderful to have you all here. As said in the description, we will be focusing in this webinar mainly on AddPath's capability to be able to do pressure wound cylindrical shapes and other features. In this webinar from Addcomposites side, it's myself, Praveen, and James Kuligowski. We will be hosting it together. So if you have any questions that you want to ask, please do put them in the chat. There is also another segment at the bottom right of the Google Meet window that allows you to post question anonymously and also participate in the polls. With that brief introduction, let me introduce the webinar. So in this webinar, we'll first briefly go through introducing the key terms. So we'll give a very brief introduction about Addcomposites and what is the technologies involved in this discussion. So AFP and filament winding. And then we'll talk about briefly about what is AddPath. As we gone through the introduction, we'll jump into the next step of the first demo, that is the how to go about planning filament winding of the tank with AddPath. As we are using a fiber placement head for winding, it enables new features. In the third section of the presentation, we'll talk about these features, and then we will share the download link for this particular beta version of the software that you can download and start using it right away. All the files that will be presented here will also be shared with you along with the recording of this webinar. So do not worry. I hope you will not miss too much. And then towards the end, we'll take questions if there are any. And please put these questions in the comment section. So with the brief introduction to the agenda, let's jump into the introduction. So this webinar is hosted by Addcomposites. And Addcomposites is born with the mission to make composites manufacturing automation accessible. And so we are a university spin-off from here in Finland. And we have about 20 plus AFP systems in the world right now, working with thermoset, thermoplastic, and dry material. In addition to AFP hardware, we also produce software for planning, simulation, digital twin, and quality control of the process. And that is what is called AddPath. That is why we are mainly focusing on that part of the product today here. The process that we'll be talking about or using the main terminologies from will be AFP, that is automated fiber placement, and filament winding. And AFP is mainly the process that focuses on getting a very flat tape unidirectional fiber placed in a particular orientation with the application of pressure and heat. Whereas in filament winding, the tow that is used is more of a bundle that is not uniform in width or thickness and is wounded a bit more based on friction compared to what you would do in AFP, which is more of close to welding. With this brief introduction to the processes that we'll be talking about, a brief introduction to AddPath. AddPath is a plugin that is built on top of Rhino. And we have built the software on top of Rhino because it's to make it highly accessible to most of technical centers and small and medium sized manufacturers who wouldn't want to pay for very expensive softwares for such thing. And what AddPath enables is definitely offline planning of 2D, 3D shapes. So you can actually create virtual production simulations, but twinning, which is basically capture the quality of the part that you're producing. So, yeah, I think with this brief introduction, I would jump into the next part. So, how to basically make a pressure wound tank with AddPath. So, I'll open AddPath here that I have. Okay. And I have set up here um, uh, basically a cylindrical tank that you would see. It could be a mandrel, it could be a liner. Um, okay. So, how would you get started? So you would go here, which is where you would go and try to add uh, a mandrel. So you can import like a step file of the liner. In this case, I have the um, pressure vessel, I call it whatever. So yeah, as you can see in the similar fashion, I imported it. So I already pre-imported it just for the sake of keeping the time short and oriented it. So I'll talk about how I went about orienting it. So I imported the file that you can see is highlighted in red here. And then I went about picking up the reference for this particular file. That is what I have chosen at this phase of the tank. So I picked up it here. I can actually go about doing it again. So you would go, yeah, I selected the origin and now start of the x-axis, clicking again. That is defining my x-axis direction. Starting of the y-axis again, and now ending of the y-axis. Okay, so now I have the mold reference created here, and I have created a custom axis that is oriented on my flange here. That is basically defining the central position of the flange and the orientation of this flange with respect to robot base. And with respect to that, I have oriented my tank at 250 millimeter away from it. Um, and after picking up the mold, selecting it and aligning it with respect to my reference, I linked it to the external axis one, which is in this case my rotary axis. Um, then I go about selecting the geometry. So in this case, I want to wind the area, and then I would go about selecting the boundary areas, which are highlighted in purple, sky blue. Yeah. And from the drop down menu on the top, I would select what type of winding I want to do. So there are many options available. In this case, I wanted to do complete tank winding with domes. So I'm selecting continuous winding, tank with domes. We'll talk about also other options that are here in the other demo that I will talk through. Once I select this, what it does, it opens a winding UI here. So I'll go to that later. So here I have defined that I want to put down 1-inch wide tape, which is 0.29 millimeter in thickness. I'm going to place it at 45-degree angle. Yeah. So I think once I have defined, like I want to do 45-degree angle winding, now I have to define and make sure that my reference for 0 and 90 is defined here. I think so. I missed that step. So I'll just quickly go back to it. It's a very critical step. So I need to make sure that I have defined my 0 degree at the beginning of the dome point, that is here. And then the dome beginning is here. So this circle center is what is defining my origin point. My zero direction is aligned with dome to dome center, and 90-degree could be just has to be perpendicular to that. Yeah. So this is very, very critical. So once, as is shown here in the diagram, with the dome, it is aligned. I'm able to start, and I need to get the D1, which is the diameter on the left side. Sorry, D underscore L. So I would go and measure it. I'll show it here. So I'm gonna pick up the point here and here. And now I have the measurement for that. And I need to do the measurement of the length again. Here I have known this value. I can also do just the measurement. And then similarly, I would go about, I can actually do the measurement. So let's go about that. Let's see if I'm able to do the measurement. Maybe not very well here. Here I'm able to select the center. Here I have some trouble selecting the center. But let's assume at the moment I'm able to select the center here. And I'm measuring the distance from this center to this center point. It's very critical that I'm measuring the starting of the dome to end of the dome, the length that I need to know. Then I have the middle section diameter that I can measure with just going to the diametrically opposite points. And then it measures it automatically. The length, once again, I'm able to measure center to center. And then the similar way, I would be able to measure the diameter here and the length here of the section, which in this case, because it's symmetric, I know. To start with, I'm just going to start with one circuit. If you want it to be completely covered, you would just put 0 circuits, and it will complete the complete coverage, and it will tell you all the values of coverage percentage, everything included. I think to start with, it's better to do maybe more than one circuit. We can do 2 circuits to see. Now we come here and we go about planning it. And now it will start planning. So you can actually see here on the top, as it starts to progress, it will do all the calculation. You would be able to see the angles, the range of these angles. And now you see the path that it has planned start to appear. It is also telling you in what angle bounds it is able to maintain the 45-degree angle that we suggested it to maintain. And it is the pattern type 2. And as we speak, it's also already started to plan the frames for the robot on this. Let's wait for a bit. I can also catch a bit of a breath here. As this is happening, I think one of the things to note is that you can see the mold here. It's actually not perfectly aligned ever. So there is a trick to see a very good simulation that I'll show in AddPath that would really give a very good visualization that does not look, it's a broken. So we are very close to seeing the tape 1 complete. Here, once again, I've gone for finer, how would I say, frame distance.
Could you explain what the frames mean and why they're important for the robot?
Yeah. So I think it's a very good point, James. Thanks. So the frames are basically asking the robot to be perpendicular to the surface, and making sure that the robot aligns the tool's forward direction with the tape's forward direction. So if you have these frames correctly planned, then your robot would come to that particular place and move in that direction. That basically ensures that you would have the placement of the tape in the right direction. And you can manipulate each of these frames. So let's say in certain section, if these frames are um, in a way that your robot will hit something, you can actually go and change this set of frames. That basically tells the robot to tilt in certain way to avoid an obstacle. So it allows you a very high degree of customization for this program that you create. Yeah, I think we are almost close to done here. Let's see as the visualization pop up. Okay, now we see the tapes. um so what I'll do now, as I said, I'll talk about a trick. So I'll hide the mold, and then I will show the mold from the geometry here. So as you can see, the now the mold looks much nicer, and it will also let me just hide this some unwanted components that I see there. So now, once we go here, what we would be able to see is very nice simulation. So let's go refresh all frames. And I set this home position to begin with. So if I say go home, so this was as a starting point that I set up at the beginning. Okay. So now as we start to play this out, let's go at a faster speed. I'm not sure how choppy is the stream, to be honest. So are you able to see?
Yeah, the stream quality is not great
Ah,
while presenting. So we'll send a recording of this directly from Rhino that you can see.
yeah. Yeah, and as I said, like all of the files that you see here would also be available to basically play around with by yourself. So I think you should also just play around with with the file for your own winding projects. So I will just go slightly faster, and that's kind of where AddPath is really good, because you just have a slider that allows you to just move past this. So here, what I'm already able to see is that the winding looks fine, and I have the control pretty much of, I'm able to do continuous winding now with the AddPath.
And sorry to interrupt, for anyone who's not familiar with AddPath, the reason that there's like a yellow one and the black one is that the yellow one is the tape that is currently being placed, and the colored ones have been previously placed.
Yeah.
And so you're able to see exactly what the tool is doing. It's just another level of visualization that we provide on AddPath.
Yeah. And in continuous winding such as this, it's not like there are two separate tapes. It's just divided into circuit. So one circuit that has been previously placed, and the current circuit that, as James mentioned, it's highlighted in yellow, that the tool is now placing. Yeah. So as this is done, this is basically, I would say, if we would have put 0 and different angle, we would see definitely different simulations. And that kind of concludes the first part of what I would call doing filament winding with AddPath. Let's jump into the next portion. James, if you see any questions, just I think we can take them towards the end. Um, yeah. So, and this is one more very great use case here. So let's focus on selective reinforcement. So, because we are using AFP head to be able to do selective. We are doing filament winding with an AFP head, so we have the possibility to cut the tape. So that allows us to do selective reinforcement. So I have a use case that I have created here. So what we can do is mainly focus on these tapes. So I created so I'll hide the certain tapes here. So we can focus on just the tape that we would like. So similar to what we saw previously, I created the importing the mold, setting up the mold, selecting the geometry. But instead of selecting the full mold, I just selected this particular area. And as a boundary, I selected this area. That's the only differentiation. And then I selected discontinuous winding path because I don't want them to continue forever. And I want them to be cut here. So I've selected discontinuous winding path. And then I selected a periphery, which is the bigger diameter here. And yeah, I've set up the 090 the same way we set it up earlier. So once we do that, and like now I have here the 45-degree angle and I programmed it, and then I got the same simulation ready. So now as we go into simulating this particular part, let's see how it does it. Now we can go faster because we have less tape in the visualization. So as you can see, this is the first tape that is getting placed here. And now you will also see how the overlaps would come. So this is the new visualization that allows you to also know exactly which layer is on the top. So it basically enables, once you are able to export in for FEA or any other analysis, it has all the corrected information about the orientation at each point. Yeah.
We did get a question. So
Okay.
how does AddPath model and deal with change in the diameter as the part becomes thicker over time?
Yeah. So it's very, very smart question here. So because we plan for AFP for thicker parts as well, there is a version where you can go and choose a module. It's at the moment it's not here loaded with me, but you can have a thick version, which is basically just gonna plan, but just for thicker parts. That basically compensates for the thickness of each tape. The very critical thing is to add a right thickness value for it, and it will take slightly longer to plan because it is basically trying to plan for very thick laminate. So it will take longer, but it will be able to compensate not only for within the same layer, but also for previous laminates thickness. So I think that is the very, very key point, to be able to know exactly where your fiber reinforcement is going to be placed. So you just need to make sure that you click on this option to compensate if you have previous laminates, and then you should request this script that we have. So this is the new module where you can request a script specifically for this particular higher thickness components, and it would allow you to create the thicker laminates much easily. Thank you for that question. It was very good question.
Thanks, Pravin. Just a note, we are only scheduled for a half hour, so if you have someplace else to be, feel free to leave and we'll send you the recording afterwards.
Awesome. So I think I will move slightly faster here. So now we go and jump into the second option. Is once again a lot of fiber steering that is we get talked about a lot, and there is a lot of benefits of fiber steered placement because you can align your fiber to your stress directions that the component is facing. So I've created an example here, and I will very quickly walk through, uh, not repeating myself, hopefully, too much. So here, the same way I imported the mold, but the only difference I have here is that I imported it with this curves that I just drew up myself in the CAD right now. But let's say if you're using FEA software, so this could be your stress factors joined together. And so these are the parts that I just imported with. And if I just choose the option user made tool parts, and I would be able to select each of these parts. Yeah, and then I would be able to, here the angle doesn't matter because the orientation is defined by the path the user chose. And yeah, I think you would be able to see the very elegant visualization here. So if I go closely here to see, you would see it's trying to follow a very steep path here. One more, and this is something, a very relatively new feature, that you would be able to analyze the steering radiuses. So as you can see for this fiber, the steering value defined is 800 millimeter. So you would, what you're seeing here is 600 millimeter steering radiuses value, which are steeper. So what you would expect here, this red indicates, is the fiber would peel off from the surface. So it may not stick. Whereas in the center section, it's okay. So even though the stress vector tells you to go along this direction, maybe this fiber width with this steering limitation may not be the best choice. So this kind of helps you tell that, hey, maybe my, even though I'm able to plan it, there is issues that I'm not seeing right now that the physicality of the material poses. So yeah, and I think that's kind of pretty much the second use case that I wanted to talk about. That now with this winding module, you're able to do is winding in a way for like steered paths. Yeah, and then
Quick
sorry.
question before we proceed for you, Pravin. So you talked about the reinforcing and building up thicknesses of just the dome ends, as well as fiber steered throughout the length of the tank itself. This is something that you can't achieve with traditional filament winding processes. So why do you think this is better or more beneficial than just winding a tank, for example?
Yeah, I think winding a tank is definitely a conventional and proven way, and it definitely allows you to create the tank that everybody else is creating today. But if you want to be able to optimize on that design, you need to be able to control where you put the material very well, and then how you put that material. So what this allows you to optimize on the, I would call, the age-old design of the tanks of the past. So this enables you to just, I guess I'll talk about from few studies. So just the dome reinforcement. There was one study that pointed that it basically reduces the amount of reinforcement that you have to apply by 35%. So if you think the most expensive part of raw material here is the reinforcement, and if you can reduce them by 35%, it's pretty remarkable. and I'm pretty sure there is still more room to go. And that's why I believe the AFP winding approach is the approach that in future many manufacturers would adopt to become and offer more competitive wounded solutions in the market. Yeah. Okay. Thank you, James, for that question. I think very well thought out. Um, and I think this is maybe the last bit, but because AFP heads are also more versatile in terms of the material that they work with, it's not about carbon or glass. It's the matrix that I'm talking about. So thermoset to thermoplastic. So as we are more talking about sustainable aviation, sustainable travel, it would start to become way more clear that thermoplastics are going to be required for their recyclability and the nature that they can be recycled and reused, and they don't need to be wasted as much as thermosets because of the shelf life. It's just bad. So I think what AFP enabled winding does is basically allows you to shift between materials at the as the your project requires. If it requires you to use more sustainable material that are thermoplastic driven that can be reused, you can very easily shift your processes to be used with not thermoset but thermoplastic or just dry material that will be infused later. Whereas with filament winding, I don't think the process is as scalable, uh, and there have been some use case shown, but with very how do you say limited applicability. So I think that's these are the three main enhanced applications that we see that is possible with uh, AFP used as a winder, and how AddPath can enable all of these. Yeah, I think as I said, the now I think we can, James, share the download link for AddPath in the chat.
Yep, I just put it in the chat, and if you can't see that, let me know, and I'll send it to you. But this will also be in the email sent out afterwards with the video recording of the webinar.
Yeah. So there will be a folder shared that basically definitely have the link to download the AddPath, but then also would have the files that are presented during this webinar. So you actually would be also able to run this on your own computer and play around for your own project. And if you have anything, we'd be more than happy to also help with your project in that regard. I think we can move to Q&A in this regard. James, is there any questions that we got that were not able to focus on?
No, it's a quiet crowd today.
That's good to hear. I think we answered all the questions. Usually not the case. Okay. But then I would just want to thank everyone for taking the time out and participating today in this uh, webinar to see how AddPath can be used for pressure wound products. And hopefully we are able to support in this regard. So please download the beta software, use it for your application. If you have any issues, let us know. We'll be more than happy to assist you with any of the issues. And if you download the beta, you'll get basically 3-month license along with it. So don't worry, you have plenty of time to use it and with your projects. Okay, yeah, I think that's it from my side. Thank you, James.
Thanks, everyone.